Welcome to the first video on ordinary differential equations. And in this video, we're going to look at an overview of what ODEs are and classify them so that by the end of this video, you will be able to classify ordinary differential equations. So what's a differential equation? Well, it's an equation that contains derivatives of an unknown function. And the solution to a differential equation is actually a function that satisfies the differential equation. So in this module, we will be looking at ordinary differential equation. And an ordinary differential equation, or ODE, is a differential equation with just one independent variable. We will be looking at differential equations for more than one independent variable in the next module when we will be talking about partial differential equations. But for now, it's just one independent variable, therefore ODEs. How do we classify ODEs? So one way to classify ODE is by their order. So the order is the order of the highest derivative that appears in the differential equation. So here's an example. A first order ODE contains a first derivative only. So that would make the ODE, I can write it in the following form, some function f of the independent variable x, the dependent variable y, and the first derivative dy dx, just the first derivative, which makes this a first order ODE, would be equal to 0. Then we can classify ODEs whether they are linear or not linear. So for a linear ODE, the function in this function f of x, y, dy, dx equal to 0 for a first order ODE, that function f is a linear function of the dependent variable y and its derivative only. Now, the independent variable x can appear in nonlinear term. The important thing is just that y and the derivative dy dx appear only in linear terms. So here's an example. Let a and b be some constant real numbers. Then the ODE dy dx plus a times x squared plus b times y equal to 0 is, well, it's linear because even though there is a ax squared term, a nonlinear term in this ODE, that nonlinear term is confined only to the independent variable x. And the dependent variable y and its derivative dy dx appear only in linear terms. Let's look at a second example. This ODE, dy dx plus a times x squared plus b times the square root of y equal to 0. Now that is nonlinear because the dependent variable y appears in a nonlinear term, the square root of y. So that's an example for a nonlinear ODE. Then we can classify ODEs whether they're homogeneous or non-homogeneous. So here's an example of a nth order ODE. So some an, some function an of x, of the independent variable, times the nth derivative of y with respect to x, plus a different function a sub n minus 1 of x, times the n minus first derivative of y with respect to x, all the way to a sub 1 of x, some other function, a function of the independent variable, times the first derivative, plus yet another function a sub naught of x, the independent variable, times the dependent variable y, is equal to some right-hand side function r of x. Now, if r of x, this right-hand side, is equal to 0, then we'll call this ODE a homogeneous ODE. And if this r of x is not always equal to 0, then this would be a non-homogeneous ODE. So let's look at a physical example of an ODE, because these ODEs that we're interested in engineering, they come from some engineering application. So here's an example. We have a tank that is filled partially with water up to a height of little h. And there is a pipe that issues water into that tank. And then there's a pipe down there at the bottom of the tank that has a little hole there where water can exit this tank. And the question is, what's the height of water in this tank at any given moment in time? Now, we have to derive here as an example what the ODE would be that describes this system. And in order to do that, to think about your fluid dynamics, you have to look at the conservation equation for mass of water in the tank. So let me write the general conservation equation for the mass of water in the tank. The change of mass of water in the tank per time unit. How can this water change? Well, it can only change through water being brought into the top pipe or water leaving through the bottom pipe. So it's the change is the mass in per time unit minus the mass out per time unit. Okay, so let's look at the change of mass of water in the tank per time unit. If m is the mass of water in the tank, the change would be dm dt, right? The derivative of the mass in the tank per time unit dt. Mass in per time unit would be dm in dt, and mass out would be per time unit would be minus dm out dt. Okay, now let's make things a little bit interesting. Let's have the inflow vary with time as this function here. So dm in dt is equal to some constant k1 plus some other constant k2 times the cosine of c times t. So somebody is opening periodically and closing periodically this inflow valve. K1, K2, and C are just real numbers. They're constants. Now, water flows out of this tank due to, well, gravity. And let's use Bernoulli's equation to figure out what that mass outflow would be. Okay, so we know that the tank is filled up to a height of h at any moment in time with water. So if we apply Bernoulli, then we'll find that the mass out per time unit, the dm out dt, would be rho times the cross-sectional area of this hole times the square root of 2 times the gravitational acceleration times the height of the water in the tank. Now, what's the total mass of water in the tank? If the cross-sectional area of the tank is A sub tank, then the total mass in the tank, if the water height is h, would be rho, the density of water, times the cross-sectional area of the tank times the height, right? The height times the cross-sectional area is the volume of water in the tank times its density is its mass. Which then means that the change of mass in the tank, dm dt, is I just have to take the time derivative of rho a tank times h. And since neither the density of water nor the cross-sectional area of the tank hopefully change, I can pull them out of the derivative, so I have rho times the cross-sectional area of the tank times dh dt. So let's put everything together into the conservation equation. So dm dt is rho times a tank times dh dt, the change of water height per time unit in the tank, is equal to dm in dt, that was my given analytical function, k1 plus k2 times the cosine of ct. And then I have minus whatever flows out, so minus rho times the cross-sectional area of the hole times the square root of 2g times the height of water in the tank. Now, in this equation, what is the dependent variable? Well, the dependent variable is h, right? The height of water in the tank. And that appears here on the left-hand side as a first derivative, so it is a first-order ODE. And it appears on the right-hand side in a square root term, which makes this ODE nonlinear. Then we have an independent variable. Which one is this in this equation? Well, that's the time t, right? We are interested in the height of water h as a function of time t, which makes t the independent variable. And that appears in the equation here, right? That's the variable with respect to which we take the derivative, and the time appears also here in the cosine term. Okay, so this is a first order nonlinear ODE that comes from the physics of this particular system. Okay, so how many solutions does this ODE have? Well, it turns out it has infinitely many solutions. To find a specific solution, we need to define an initial condition, or also called a constraint on the solution. Now, what is this initial condition? Well, it's basically what is the height of water inside of the tank at a known moment in time. So we have to define the dependent variable value at a specified value of the independent variable value. Now, this is a first order ODE, so this will require just one constraint. And since ODEs from physical systems and engineering oftentimes involve time as the independent variable, we will call these ODEs initial value problem because this constraint is given at an initial time value. So in this example here, I need at some time t0, some initial time t0, I must know what the height of water is in this tank, h sub 0. And both t0 and h0, their values have to be provided. You can write this as h of t0 equal to h0 as well. Now, let's look at the general form of a first order ODE. First order ODE meant I only have the first derivative, and so that would be dy dx is equal to a function of the independent variable x and the dependent variable y. And I need a constraint, so y at some known value x1 is equal to some second known value y1. Now, can we interpret this first order ODE geometrically? So what does this equation say? Well, it basically says at every point xy, right, I can evaluate the right-hand side f of xy, because that's a function that has to be given in the ODE. And that f of xy is equal to the first derivative dy dx. But what is the geometric interpretation of dy dx, the first derivative? Well, it's a slope, right? The slope of y of x is dy dx. So at every data pair x and y, the f of xy gives me the slope of the function y of x. So let's have an example here. Dy dx is equal to f of x and y. And let's just have an example that f of xy is equal to minus 1.2 times y plus 7 times e to the power negative 0.3 times x, which would be a linear first order ODE. And let me constrain my solution domain between 0 and 4 for x and 2 and 6 for y, just so that I can fit something here onto the slide. Now, I can evaluate this f, right, at data pairs of x and y, which I have done here. And I know that this f of xy is supposed to give me the slope of the function y at that point. So what's done here is I've drawn line segments at combinations of x and y values that show me what the value of this local slope is. Now, the slopes we know are the slopes of the function y of x. So they have to be tangent to the solution y of x. So these slopes here, these lines, show me the direction that y of x follows as a geometrical interpretation of this ODE. But there are, of course, infinitely many solutions, and in order to pick a particular solution, I need to provide an initial condition or a constraint. So let's look at the solutions for 3 different initial conditions. The first one is that y at x equal to 0 is equal to 3. So x equal to 0, y equal to 3. If I draw this in this graph here, that would be this red point here. Okay? And now I know that my solution follows the direction given by these line segments that indicate the local slope. So if I kind of try to follow this along here graphically, that would be my function y of x that is always tangent here to these indicated slope values. So that would be the solution y of x to this ODE with the initial constraint y of 0 is equal to 3. Let's look at a second one. Let's have if x is equal to 1.5, then y shall be equal to 2. So that would be this particular point here, down there. And if I follow the tangent lines, that would be the solution that has this particular initial condition. And finally, let's look at a third example. If x is equal to 2, y of 2 is supposed to be equal to 6. So that would be 2, 6 would be this blue point up there. And my solution would follow graphically, geometrically, right, these tangent lines indicated by the slope segments. And that would be the solution graphically that I could determine that way. So that's a graphical interpretation of a first order ODE because the first derivative just gives me the local slope of the solution. Thank you for watching.